This video will identify inner and outer functions, develop chain rule, and find the derivative of sine of x cubed. This is the 3.4 pre-class video. Alright, we'll start with reviewing composition of functions. I'll put 4 examples here: sine of cosine of x, tangent of x cubed, e raised to the x squared plus 3, and the square root of 9 minus x squared. Now, each one of these examples is a composition of functions because there's one function inside of another function. The way we can write that is, well, the whole function itself we'll call capital H, but that can be thought of as an inner function inside of an outer function. The inner function is g of x and the outer function is f. So we can think of each one of these functions h as composed of an inner function and an outer function. Let's clarify this a little bit more. So we'll call the outer function f of u and the inner function to be g of x, so that if you substitute g of x in for u, you get f of g of x. So in the first case, f of u would be sine of u, and g of x would be cosine of x. Right? Notice if you let u equal to g of x, then we would get sine of cosine of x. The outer function is sine, the inner function is cosine of x. For the next one, the outer function would be tangent of u, and then the inner function is x cubed. Outer function for the next one is e to the u. That's because x squared plus 3 is inside of the exponential function, right? X squared plus 3 is g of x, the inner function. And next, the square root of u is the outer function. The inner function is 9 minus x squared. All right, we've identified inner and outer functions for a composition of functions, but our main task is to figure out what is the derivative of capital H, right? What's the derivative of a composition of functions? Well, we haven't done this before. We don't have a rule, we don't have a derivative rule to figure out what's the derivative of a composition of functions. So that's what we'll work on next. The rule for taking a derivative of a composition of functions is called chain rule, and we'll take an intuitive approach to developing this rule. So think about this. If f changes 10 times faster than u, and u changes 5 times faster than x, then f changes how much faster than x? Take a moment to think about that one. If f changes 10 times faster than u, and u changes 5 times faster than x, then f changes 50 times faster than x. If that's not quite intuitive for you, for me it helps to think about one car driving faster than another car, and then it helps me think of, oh, I need to multiply these two numbers together, and so that f is changing 50 times faster than x. Now let's use a little bit of mathematical notation to describe what's happening. We can think about f changing 10 times faster than u as the ratio of the change in f and the change of u, right? The change of f divided by the change of u would be 10. That's because f is changing 10 times faster than u. And likewise for the change of u divided by the change of x, that would be 5. And then we figured out that the change in f divided by the change of x is 50. And we did that by multiplying 10 and 5 together, which would be multiplying delta f divided by delta u with delta u divided by delta x. But let's go a little bit further with our notation. Instead of change of f divided by change of u, we can think about the instantaneous rate of change of f with respect to u, and that'd be 10. And likewise with instantaneous rate of change of u with respect to x. And what we solved for, we can think about as the instantaneous rate of change of f with respect to x. Now it's the product of those two rates of change, which gave us 50. Alright, so that's the bit of intuitive part that we'll use in a moment when developing the chain rule. We almost have chain rule here, but we've got to use our notation with functions. So let h of x equal to f of u, where u is equal to g of x, just like before, because if u is equal to g of x, then f of u is f of g of x. Alright, we want to take the derivative of h with respect to x. Right? That's our whole goal for this video, is because we don't know how to take derivative of composition of functions. And h is a composition of functions. But remember, h is equal to f of u, so this is equivalent to taking the derivative of f with respect to x. This is where our bit of intuitive information from above comes into play, because we said the derivative of f with respect to x is equal to the product of those two rates of change. So derivative of f with respect to x is equal to derivative of f with respect to u times derivative of u with respect to x. And we're almost done, but we're just going to write it a little bit cleaner. So we'll use prime notation, f prime of u times u prime of x. And then u is equal to g of x, so we can substitute that in for u. And so it's f prime of g of x, right, because it's f prime of u. And then times g prime of x, because we were multiplying by u prime of x. So that's timesing g prime of x. And there we have it. This is chain rule. the derivative of h of x, where h of x is equal to f of g of x, right? Composition of functions, that is equal to the derivative of f of g of x multiplied by the derivative of g of x. This rule is pretty complicated, and it's a good idea to get lots of practice on chain rule. We'll look at one example, but you'll do a lot of examples in class. So let's look at one example using chain rule. Let's put chain rule on the right-hand side for reference, and let h of x equal to sine of x cubed. And we need to identify our outer function and our inner function. All right, so outer function is sine of u, inner function is x cubed. We're going to take the derivatives of both. So derivative of sine of u is cosine of u, and the derivative of x cubed is 3x squared. And that's all we need for chain rule. So there it is. The derivative of h is cosine of x cubed multiplied by 3x squared. So notice cosine of x cubed, that's the derivative of f with g of x on the inside. Then we're multiplying by the derivative of g. All right, that's it for this video. Hopefully those objectives warmed you up for class.